Hi, and welcome to another video on scalar fields. What we're going to do in this video is we're going to look at patterns on scalar fields, and then using some of the concepts that we developed, we are going to try to identify those patterns on weather charts. So some of the patterns that you probably are familiar with already are things like highs and lows, and then we're going to talk about ridges and troughs, and then calls and also waves. Now with highs and lows, you're probably more familiar with highs and lows as far as pressure, but you can use these concepts or these patterns for any type of scalar field. You can look at highs of temperature, highs of precipitation amount, highs of dew point, and likewise you can also identify lows of density or lows of pressure change or things like that. So we're going to go through all of these different definitions, and then they can be applied to any scalar field. First, before we define any of these concepts, we have to look at isopleths and then curved isopleths and then define whether the radius, in other words, from the center of the curve or the circle outward, how does the pressure or how does the values change? And then based on that, we can define our radius of curvature as either positive or negative. So as you move out from a circle, and if the values get bigger, in this case you can see values going from 552 to 558 to 564. If you see that, then we define the radius of curvature as positive. Conversely, if the values decrease as you move outwards from the center, then we define the radius of curvature negative. And this is an important consideration. We'll use this in defining ridges and troughs. So first off, we're going to start with highs, and then we'll work our way into lows. There's some mathematics behind this. I put those at the bottom, but you really don't have to be concerned with that, except when you get to higher meteorological classes. If you take a senior level class, you will talk about this. But what a high is, by definition, it's a maximum in the scalar field. The value is maximum. And usually there's one closed isopleth to define the high. In other words, there's a line that circles the high, as you can see on this map. And mathematically, what it represents, the high, it means right at that point, the gradient in pressure, temperature, anything, the gradient is zero right at that point. But there's a change in the gradient. And we haven't talked about gradients yet, but I thought I'd just put that out there. That's what that mathematical representation means at the bottom. But don't get too concerned about the mathematics. A low, by definition, means that there's a minimum, a local minimum in the scalar field. Once again, we also represent a low with a closed isopleth around the low. It's not a requirement, but typically that's what we show. And then also it means that the gradient right at the center of the low is zero, but there is a change in the gradient. And that's what that mathematical representation is at the bottom there. A lot of times when computers generate highs and lows, they're looking at just in a local area how the values change. And a lot of times they don't look at the big picture. Computers don't look at the big picture. And as a result, they put highs and lows everywhere. And in meteorology, we commonly call these spurious or weak highs and lows. They are probably there, but they're really not significant to the weather pattern, so we ignore them. And when you do your analysis, you won't be putting these highs and lows right next to each other, but computers do that. So I just want you to be aware of that. Typically when you see that, we either ignore it or recognize that that one big area has a big high, or that one big area, as represented here, has a low, and we don't need to put all those little lows there. And now onto ridges and troughs. A trough is a line that connects points with relatively maximum positive curvature. Remember, positive curvature means that as you move out from the center of the values increase. So as you move away, the values increase. In other words, to put it more simply, these isopleths bend around lower values. So here's an example. This is one that I drew, and the mathematical representation of a trough is over on the left side. Has to do with partial derivatives, in other words, how a value changes in the x direction, and then how the change in the value changes in the x direction. I know that's kind of confusing. Don't worry too much about that. Just know that a trough is a region of relatively lower values. And we usually talk about pressure or heights, but it also could be temperature, dew points, anything actually. But more commonly, we do talk about pressure, lower pressure or lower heights in a region.
An inverted trough is one that has an easterly component of motion, meaning that the trough itself moves from the east to the west. Typically, inverted troughs are found in the northern hemisphere on the northern side of a low pressure system like you see here in this figure or in this weather map. Inverted troughs are very important because that's where typically you find the heaviest precipitation. In the northern hemisphere, low pressure systems like the one you see here move from the west to the east, but the trough in this case would be moving, the inverted trough would be moving from the east to the west. So it's the exactly opposite the direction that the low is moving. So in other words, the trough can stay over a region for an extended period of time because its westward motion is offset by the eastward movement of the low. And as a result, that's where you see a lot of heavy precipitation. And specifically during the wintertime, you'll see heavy snow bands right along that inverted trough. So they're important.
So another thing that's important is negatively or positively tilted troughs. Negatively tilted troughs are ones that are, how would I say this? They as you move towards the south, they tilt towards the east. And that's what a negatively tilted trough looks like. Specifically, we usually look at troughs in the upper atmosphere, looking at heights, looking at contours, and we'll identify these. And we'll go through an example here shortly, and you'll also go through an example in lab. Here's a positively tilted trough, so that as you go towards the south, it's kind of tilted back towards the west. Positively and negatively tilted troughs are important because typically negatively tilted troughs have a little bit more energy. They're very important in identifying where severe weather will develop in short periods of time.
Here's an example of two positively tilted troughs. And you can see that the positively tilted troughs have a component of motion towards the south. Typically, positively tilted troughs are ones that are usually very young and they're still developing or maturing. Negatively tilted troughs are ones that have matured and you start to see some cold air advection moving over warmer air. In other words, the cold air is advancing rapidly aloft. That tends to destabilize the atmosphere, as you recall from our discussion on skew T log P and this destabilization of the atmosphere.
And then we talked about troughs. The converse of that is the ridge, and it's a line that connects points with relatively maximum negative curvature. So as you move out from the center of the high, you'll see values getting lower and lower. That's what that means by negative curvature. So that's kind of complicated, but if you want the basic general definition, it's where isopleths bend around higher values. It's an extension you can think of higher values of whatever, pressure, heights, temperature, anything. So there's the mathematical representation of the ridge. We use a squiggle line to represent a ridge, a dashed line for a trough. And in this case, the mathematics say that right at the trough line, or the ridge line, I should say, not the trough, but the ridge line, there is no pressure gradient, but there is a change in the pressure gradient, or height gradient, actually. That's what that mathematics says. So here's a little exercise in helping identify troughs and ridges. So let's find the troughs. Where are all the troughs? So you look for anywhere where the lines curve. And if it's an extension of low, if you see the low extending through that region, that would be a trough. So can you identify the troughs? And here's the solution. Shows wherever there's a curve, there's a trough. Now with ridges, you'll see lots of curves also extending out from highs, and those would be ridges. And that's how we identify ridges. You'll have this exercise in class. You get to do this on an assignment or on a worksheet. Okay, a couple other definitions quickly. What is a call? A call is a hyperbolic point between pairs of highs and lows. Typically, this is an area where you see frontogenesis, and we'll talk more about that when we get into fronts. And then a wave train is a sequence of ridges and troughs that move along with the flow. So looking down on the North Pole, this is a 500 millibar map that shows the change, or shows you heights at 500 millibars, the height of the 500 millibar surface. And you see that there are regions where there are troughs and regions where there are ridges. Typically, we only identify the troughs, but this helps us show the wave sequence around the northern hemisphere. All of these troughs are moving from the west to the east, and we can identify those as they move through the flow. And then a wave is a cycle of alternating troughs and ridges. And you can have long waves or short waves. Long waves typically are major troughs and ridges, and they have a very long wavelength and also typically significant amplitude. And we call these also planetary waves. And this is what we were just looking at on the previous chart. Looking down on the North Pole, you can see those big ridges and big troughs. But then superimposed upon these big ridges and troughs are smaller ones, which we call short waves. And these short waves move a little bit faster, and they move actually through the long waves. And here's some examples of short waves. There you go. And these short waves are what gives us weather over a period of a day or less, whereas long waves give us a general weather pattern for maybe a week or 3 or 4 days or something like that. So that's a summary of all the different types of patterns that we can see in the atmosphere. In another PowerPoint and another video, we'll talk about how we describe these patterns.